Hello everyone. Uh, in the last session, we spoke about what do we mean by degeneracy, and we understood degeneracy through a numerical problem. That time we discussed that we will be solving such problems. For solving it, first we need to get rid of the degeneracy, and then subsequently find the optimal solution, right? So in this session, we will see with the same numerical example, how do we get rid of that degeneracy, and subsequently, how do we solve it optimally. So we'll go to that same numerical problem. These were the costs, and we had that time arrived at some solution for that. Let me write those solution. Whatever numbers are written here, these are basically your cost. And now we will write those allocations in this. So in the first row, there was an allocation here and here. Then we had an allocation of 10 units here, 20 units here, here 20 units, and here there were 25 units, and this was having 5 units. And then in the previous session, we also said that since the number of allocations here, 1, 2, 3, 4, 5, 6, 7, 7 only, against the requirement of m plus n minus 1. In this case, m plus n minus 1 was number of rows. There are 4 rows and then 5 columns, and it was working out to 8. Since the actual number of allocations was less than the desired number of allocations, we said that this was a degenerate basic feasible solution. Now, in order to remove the degeneracy, what we do is we introduce a quantity epsilon. The symbol is epsilon, which is a positive quantity, but it is very smaller quantity, means it is almost tending to 0. So this epsilon, we need to bring it to any of the unallocated cell so that we meet that particular condition, that is m plus n minus 1. By that, we try to get rid of that degeneracy. So generally, this epsilon is allocated to that particular cell where the cost is least, right? So if you look into the unallocated cells here, the cost is 10, here it is 15, here it is 9, 5, 10, 15, 5, 14, 7, 20, and here nothing, right? So here it is actually capital M. Last time we wrote that also, means M is actually tending to infinity, because there was a restriction in this particular problem, and for that reason we took this as capital M. Means you are assigning a very larger cost in this so that no allocation will be done. Of course, there is no allocation here. So in these unallocated cells, generally we choose that particular cell which has got a least cost. So either I can choose this 5, because 5 is the least now, this 5 or this 5. But since already there are 2 allocations in this row, let me choose this 5 as the unallocated cell where I will be allocating now this epsilon. Now let us do the UV method, wherein number of rows, depending on number of rows, that many number of UIs will be there. So this is U1, U2, then you have U3, then you have U4. Similarly, depending on the number of columns, we will have VJs. First one will be V1, V2, V3, V4, and V5. To start with, we always consider this U1 as 0, and then we try to find out the rest of the UIs and VJs. So since this is the first allocated cell, 0 plus something, I should get this 2, so that something should be 2 here. Then 0 plus something, I should get this 3. So that something should be 3 here. Now, below this, let us come. There is an allocation here. 2 plus something, I should get this 5. So that something should be 3. 3 plus something, I should get 15. So this something should be 12. Then 3 plus something, I should get this 13. So that something should be 10. There is an allocation here. 10 plus something, I should get this 8. So this something should be minus 2. Minus 2 plus something, I should get this 4. So this something should be 6. 6 plus something, I should get this 2. So this something should be minus 4. Now we got all the UIs and VJs. Now we can calculate delta IJs for all unallocated cells. So all the unallocated cells, we will be drawing this brackets so that inside brackets we will fill in the delta values. So how do we calculate delta IJs within brackets? It is nothing but Cij minus of Ui plus Vj. Means we have to add the corresponding U and V and then subtract it from the relevant cost. For example, in the first case, U and V, if I add, that is 0 plus 12, it is 12. Then 10 minus 12, it becomes minus 2. Moving on to the next one, 0 minus 4, it is minus 4. Then 15 minus of minus 4, it becomes 15 plus 4. So it is 19. Then here 0 minus 2, it is minus 2. 9 minus of minus 2, it becomes 9 plus 2. So it is 11. Here it is 6 plus 12, it is 18. 5 minus 18, it becomes negative 13. 6 plus 2, it is 8. 10 minus 8 is 2. Here it is 6 plus 3, 9. 15 minus 9 becomes 6. Here 3 plus 3, 6. 14 minus 6, it is 8. Here 3 minus 4, it is negative 1. Then 7 minus or minus 1, it is 7 plus 1. So it becomes 8. Here 3 minus 2, it is 1. 15 minus 1 is 14. 10 plus 12, it is 22. 20 minus 22, it is minus 2. 10 plus 2, it is 12. 15 minus 12, it is 3. 10 minus 4, it is 6. Then m minus 6. M itself is a larger number, means it is an infinity. Infinity minus a smaller number 6 will again lead to infinity only. So we can simply write that as capital M. Now, is this an optimal solution? No, because there are some of the delta Ij's which has got negative sign in it. Here it is negative 2, here it is negative 3, here it is negative 2. Means how do we proceed with the most negative delta Ij cell, that is this cell, we have to assign a quantity called theta. Assign theta to the most negative delta Ij. So we will be assigning that theta to this negative 13, that particular cell. Means first row, second row, first column. So let us do that. So here again, once again, I will write those allocations. Here we had 20 as the allocation. Here we had 5 as the allocation. Then we decided that we'll be assigning a quantity theta here. Then here we had 10 as the allocation. Here we had 20 as the allocation. Then we had here 20 as the allocation. Then here we had that epsilon what we introduced. Here we had 25 as the allocation. Here we had 5 as the allocation. Now we had assigned a theta here, but this column total should be 20 only because the corresponding demand quantity in this particular question was 20 only. That means if I put this theta here, this will exceed 20. That should not happen. That means if I assign a theta here, that that much I should subtract it here. Since I subtracted a theta here, I should add a theta here. Since I added a theta here, I should subtract the same quantity theta here. Since I subtracted here, I should add that same quantity here. Since I added here, I should subtract the same quantity here. Since I subtracted the theta here, I should add here. Then I should subtract it here. Already there is a theta here. That means everywhere, for example, here there is a minus theta plus theta minus theta plus theta minus theta plus theta minus theta. Means all the row supply quantities will be the same whatever it was earlier. Now coming to columns, plus minus theta plus theta plus theta minus theta plus theta. Now this will definitely serve our purpose that the quantities, supply quantities and demand quantities do not change. It remains as it is. Now what is the maximum value what theta can take? Maximum value of theta is equal to, so wherever theta is getting subtracted, we will compare those numbers. Here it is 20 minus theta, 20 minus theta, 20 minus theta, 25 minus theta. That means the maximum value what theta can take is 20 only, because it can't take 25. If I put 25, what will happen? These numbers will become negative, whereas quantities cannot be negative. So I should consider the maximum value of theta as 20 only. So based on this theta value, we will create the new table and write there the quantities, the revised quantities or new allocated quantities. Let us do that. So what will happen now? Here it will become 25, and then here it will become 20. Here it will be 10. Here it will be 20. Here it will be 5. This will be 25. So let us once again check. 20 minus theta means 20 minus 20. That has to become 0. So that's why I didn't write anything. 5 plus theta means 5 plus 20. It becomes 25. That's why I wrote 25 here. Then here it is 20. Here it is 10. Here it is 0. Means 20 and 10. 20 and 10. Then here 20 minus 20. It becomes 0. Epsilon plus theta. Epsilon is a quantity which is very nearer to 0. So that means even if I add that quantity with this theta, theta is 20, it will remain as 20 only. That's why I didn't write anything. I just simply wrote 20. Means epsilon, very small quantity, which is almost equivalent to 0, plus this 20, I will get 20. Then coming to the next 25 minus theta, it is 20. I'm sorry, 25 minus 20, it becomes 5. Here it becomes 25. Means this will be 5 and this will be 25. Let's check. 5 and 25. Now number of allocations. 1, 2, 3, 4, 5, 6. Suddenly, earlier we had 7 allocations in the beginning. Just to bring it to 8 allocations, we introduced epsilon in a particular area, in a particular cell. And now again it has come down to 6, not even 7, it has come down to 6. That means in 2 places we need to introduce epsilon. So what we will do, we will directly start with ui's and vj's. u1, we consider generally u1 as 0. Then we find out the other ui's and vj's. Here it is v1, v2, v3, v4, v5, right. Now let us find out whatever is possible. 0 plus something, I should get this 3, so that something should be 3 here. Now coming down, there is an allocation. 3 plus something, I should get 13. That means this something should be 10. 10 plus something, I should get this 8. So that something should be here -2. Anything else we can find? We can't find this. Reason is we don't have this U2 value. We can't find this because we don't have the U2 value. We can't find this because we don't have the U3 value. Right? Now we have to definitely introduce epsilon. One epsilon where we can introduce is to the least cost cell, which is of course 2. If you compare all the costs, 2 is the least cost in the unallocated cells. So first I will introduce an epsilon here. Since I introduce epsilon here, let me calculate this. 0 plus something, I should get 2. So that something should be 2 only. Coming down, there is an allocation here. 2 plus something, I should get this 5. So that something should be 3 here. Right? So what are left now? U2 and V4 is left. Means if I have to calculate, if I have to calculate U2, then either I should have this value to be assigned as epsilon, or this value to be assigned as an epsilon, or this value to be assigned as an epsilon. Which one we will choose? Let's do like this. In the first row, there are already 2 allocations, epsilon and 25. In second row, already 2 allocations are there, 20 and 10. In the third row, only 1 allocation. In the last row, 2 allocations are there. Now coming to column, if you look into this first column, only 1 allocation. Second column, 2 allocations. Third, 2 allocations. Fourth, there is only 1 allocation. Last, there is only 1 allocation. So, I mean, wherever we can increase the number of allocation, we can see that. Again, going back to your row, first row already 2 allocations, let me not do any more allocation there. Second row already 2 allocations, let me not do any more there. Third, only 1 allocation, let me try there where we can allocate. If I allocate here, already there is only 1 allocation possible. Here already 2 allocations are there, don't do that. Here, yes, it is possible. Here it is possible because only 1 allocation. But again, if you look into these costs, 15, 14, 7 and 15, the least is 7. So it is better to allocate it here. Let me allocate, because that is the least cost among in this row. Let me allocate the epsilon there. If I do that, I can able to now find out what is V4. 3 plus something, I should get the 7. So that something should be 4 here. Again, remember, allocating epsilon is arbitrarily done. It is all hit and trial type only. But generally, we prefer to allocate epsilon to that particular cell which has got a least cost in it. That's what generally we try to do. Now, so since I allocated epsilon here, I could find out this 4 now, because 3 plus 4, I got this 7. Now again, there is an allocation here. 4 plus something, I will get this 2. That means that something should be -2 here. Now that I got this -2 plus something, I should get this 5. That means this has to be 7. We can recheck once again. For all allocated cells, we can check the totals. 0 plus 2, it is 2. 0 plus 3, it is 3. Next here, 7 minus 2, it is 5. Then 4 minus 2, it is 2. Then 4 plus 3, it is 7. 2 plus 3, it is 5. And then 3 plus 10, it is 13. 10 minus 2, it is 8. So everything is matching. Now let us find out the delta ij's for all the unallocated cells. Let me put brackets in all the unallocated cells. Then we will calculate the value of each. Right. So first one, 0 plus 7, it is 7. 10 minus 7 is 3. Here, 0 plus 4, it is 4. 15 minus 4 is 11. 0 minus 2, it is -2. 9 minus or minus 2, it becomes 9 plus 2. So it is 11. Here, Minus 2 plus 2, it is 0. 10 minus 0 is 10. 3 minus 2, it is 1. 15 minus 1 is 14. Minus 2, it is minus 4. 4 minus a minus 4, it is 4 plus 4, it becomes 8. 3 plus 7, it is 10. 15 minus 10 is 5. 3 plus 3, it is 6. 14 minus 6 is 8. 3 minus 2, it is 1. 15 minus 1 is 14. 10 plus 7, it is 17. 20 minus 17, it is 3. 10 plus 2, it is 12. 15 minus 12 is 3. Then 10 plus 4, it is 14. Here we had m, isn't it? We had that m. So 10 plus 4, it is 14. M minus 14, m itself is a very large number, means like infinity. Infinity minus 14 will be infinity only. So again, I will write only m. So now we can note all delta ij's. Means whatever numbers which are within the brackets are exceeding 0. And hence we can say we reached optimality. So we know how to present this solution wherein we calculate. So I'm not going into that because already we had seen 2-3 times how to present the optimal solution. So this allocation, since all the delta ij's are greater than 0, we can conclude that we reached the optimality. In case if you want to calculate the cost, we can straight away go to that particular allocation. Means 2 into epsilon. Epsilon is considered to be 0, so it is 0 only. Then 3 into 25, it becomes 75. Then 5 into 20, it becomes 100. So 75 plus 100, we will add. Like that, we proceed calculating the optimal solution, right? So if you want, we can calculate it. We'll try to calculate it here itself. Total cost is equal to, means 2 into epsilon. So that is 2 into 0 only. So I'll put it as 0. Then 3 into 25. So that becomes 75. Then 5 into 20, it is 100. Then 2 into 10, it is 20. Plus 5 into 20, it is 100. Plus 7 into epsilon. 7 into epsilon is tending to 0. That means 7 into 0, it is 0 only. Then 8 into 25, that is 200. So we can add up this. I think it will work out to 200 plus 100, 300, 400, 495. And since all these costs, I think in the original problem, it was in terms of hundreds, I think. One more is there, I think I missed it. 13 into 5. So let me write that also. Means prior to 8 into 25, which is 200, there is 13 into 5 also, which works out to 65. So this will get added with this. So this will be 10, 7, 5. Or actually, since everything was given in terms of, is it 560? I'm sorry. So it is 560. And since everything is given, the cost in the table is given in terms of 100. So we'll have to say 56, 0, and then double zeros will add. So it is 56,000 will be our total cost. Anyway, you can formally write the presenting the solution by writing those x, the location means this will be written as x13, means like this. Allocation, you will write x13 equal to 25, and then cost per unit is 3. and then you will show that 2 into 3, 25 into 3, that is working out to 75. Like that, you can present it properly. So in this video, overall what we had seen is, if at all, if we come across with the degeneracy in a transportation problem's initial basic feasible solution, how do we get rid of this? By bringing in a positive quantity, but which is very low quantity called epsilon. That's why we write epsilon is greater than 0, but epsilon tends to infinity. To any of the unallocated cell, preferably a cell which has got a very least cost. In that cell, we try to introduce it. Then we proceed with our UV method to find out whether it is optimal or not. If not optimal, then we bring in that theta method to identify what can be the maximum value of the theta, and then substitute the values. Again, once again, go with finding out whether it is matching with the m plus n minus 1 or not. If not, that many number of cells, you have to bring in that epsilon. Here in this case, we got 6 allocations instead of 8 allocations what we are requiring. So in 2 places we brought in epsilon, one is here and one is here, and then try to find out again the ui's and vj's, and then subsequently found out delta ij's, and we found that all the delta ij's are positive, and hence we concluded that we reached the optimal solution. And you know very well how to calculate the total cost, which we did it here roughly. And the allocations, if you want to present it properly, generally we use this symbol X for allocation, and this is basically the location. What is the row and what is the column that is coming as a suffix in the X, in the notation X. We write it as a suffix. That suffix is actually indicating the position of that particular allocation, which row and which column. First number represents row, second number represents column. So that's about your degeneracy, and that too, this particular problem is degeneracy with a restriction in the transportation. That is why we put this capital M over here, means no allocation should happen to that particular cell, right? So that's all for today in this session. I'll see you again in the next video. In case if you find this video to be useful, based on the contents, whatever is available, I would request you to like, share with your friends, and please do subscribe to my video so that you can get regular updates about my forthcoming videos. Thanks a lot. Till then, bye.